If what is arriving over the Pacific Northwest right now has you paying attention the way it has me, hit like and subscribe to Signal Watch, because this story is going to develop fast, and you do not want to miss what comes next. Drop a comment below. Tell me where you're watching from, what the temperature is right now where you live, and this: does your home have air conditioning? Because where you answer that question from changes everything about this event. And if you know someone in the Pacific Northwest or British Columbia, a family member, a friend, anyone, share this video with them right now. On X, on Facebook, in a direct message. What we're covering today could matter. You are the reason we can keep doing this. Thank you. Here's what this investigation covers: the atmospheric physics behind a heat dome that current forecast models show pushing temperatures 30 to 40 degrees above seasonal averages across a region that has no physiological, architectural, or electrical infrastructure designed to handle it. The feedback loop between a record dry winter, evaporated soil moisture, and what happens to forests when a heat event arrives without any buffer. The grid reliability gap that was formally documented by a consulting firm commissioned by the region's own utilities. A gap that exists right now, today, in 2026, before one single air conditioner gets switched on. And what the 2021 Pacific Northwest heat dome tells us about who dies when a region this unprepared meets temperatures this extreme. Now, let's get into it. There's a mass of air above the Pacific Northwest right now, and it is not behaving the way air above this region is supposed to behave in this season. Normally, the Pacific Northwest in late spring and early summer is governed by marine influence. The North Pacific Ocean, vast cold relative to land and perpetually churning, keeps a lid on temperatures west of the Cascades. Cool, moist air flows on shore. The Cascade and coast ranges funnel and moderate it. Cities like Seattle and Portland sit in the low to mid-70s Fahrenheit through most of June and into July. Temperatures mild enough that generations of Pacific Northwesterners never needed to install air conditioning, never thought much about heat as a mortal threat, never built their homes or their infrastructure around the assumption that it could become one. That moderation is failing right now. A massive high-pressure ridge is building, or has built, over the region. High-pressure systems in the atmosphere are regions where air at altitude descends toward the surface. And when air descends, it compresses. Compressed air heats up. That is not a metaphor. It is the physics of adiabatic compression, the same process that makes a bicycle pump barrel warm when you push air through it, scaled up to the size of the troposphere. Descending air in a high-pressure system warms at a rate of roughly 10 degrees Celsius per kilometer of descent, the dry adiabatic lapse rate. When that sinking, compressing column of air is also being reinforced by the dynamics of a blocking pattern that prevents the atmosphere's normal eastward flow from sweeping the system away, the result is sustained, progressive, compounding heat at the surface. The specific atmospheric configuration responsible for the most extreme heat events in the Western Hemisphere has a name. It is called an omega block, named for the Greek letter it resembles when drawn on an upper atmosphere pressure map. A strong high-pressure ridge, flanked by two low-pressure troughs on either side, creates a pattern that the atmosphere cannot easily self-correct. Blocking events of this type are identified at the 500 millibar pressure level, roughly 5,500 meters of altitude, where unusually elevated geopotential heights persisting for 5 days or more mark the atmosphere as effectively frozen in place. Normal weather systems, which ordinarily progress eastward, driven by the jet stream, cannot break through the block. They pile up on either side of it and stall. And below the block, the heat accumulates. The same atmospheric configuration, the omega block over the Pacific Northwest and British Columbia, was the primary meteorological driver of the June 2021 Pacific Northwest heat dome, the event that killed more than 900 people across the region and registered as one of the most extreme heat events ever recorded globally relative to baseline temperatures. The 2022 peer-reviewed paper in Science Advances that formally examined the 2021 event placed it at over 4 standard deviations above the historical mean, and noted that only 5 other heat waves recorded globally since 1960 had been more extreme in that measure. That paper's finding is worth staying with. 4 standard deviations. In a normally distributed system, an event 4 standard deviations from the mean has a probability of occurrence of roughly 1 in 31,000. Portland reached 116 degrees Fahrenheit on June 28, 2021, shattering its own previous all-time record of 107 by 9 degrees. Not a tenth of a degree, not even a degree, 9 degrees, and set that record for 3 consecutive days. The system now building over the Pacific Northwest carries the same atmospheric fingerprint as 2021, with one crucial additional ingredient. The background onto which this event is arriving is substantially more vulnerable than the one 2021 hit, and we'll come back to that. First, let's go inside the physics of what a heat dome actually does to the air you breathe. One more number before we move to the physics, because it frames everything that follows. The March 2026 early season Western Heat event, the record-shattering dome that covered the southwestern United States before the system migrated north, was analyzed in real time by atmospheric scientists at California Water Research, who published a detailed technical breakdown within days of its peak. Their conclusion? The March 2026 event shared a key physical mechanism with the June 2021 Pacific Northwest heat dome. Downstream ridge amplification driven by upstream latent heat release. This is not a coincidence. It is a signature. The same atmospheric engine that killed 900 people in the Pacific Northwest and British Columbia in 5 days in June 2021 has been demonstrably operational in the region's atmospheric system again in 2026, and now it is moving north. The compression of descending air under a high-pressure ridge is only the first of several reinforcing mechanisms that make an established heat dome so difficult to break and so lethal while it persists. When air sinks and warms under the ridge, it suppresses convection, the process by which warm surface air rises, cools, and forms clouds. Clouds perform 2 functions that are critical to surface temperature regulation. They reflect incoming solar radiation before it reaches the ground, and they signal the movement of moisture through the lower atmosphere. Suppress convection, and you suppress both. The result, under an established heat dome, is clear, cloudless skies and unimpeded solar radiation reaching the surface day after day. Every hour of those cloudless days adds additional heat load to the surface that, without convection, to vent it, has nowhere to go but further into buildings, roads, and human bodies. The sun angle matters. In late spring and early summer at the latitude of Seattle and Portland, roughly 45 to 48 degrees north, the sun is high in the sky. Solar radiation arrives at a favorable angle for heating land surfaces. Under a heat dome, that angle and intensity combine with the absence of cloud cover to create a radiative heating regime at the surface that can push actual ground level temperatures well above what the official air temperature, measured in shade at standard height, reports. Asphalt surfaces can reach temperatures approaching 70 or 80 degrees Celsius during peak heat dome conditions. Metal surfaces higher still. The overnight recovery that normally breaks heat stress accumulation, the cooling that happens in temperate climates when the sun goes down and the surface radiates its stored heat upward into a clear sky, also fails under a heat dome. The mechanism is simple. Long-wave radiation emitted by the warm surface would normally escape to space at night, allowing the air near the surface to cool. Under a high-pressure blocking pattern, with descending warm air above serving as a partial radiative blanket, nighttime cooling is suppressed. Minimum temperatures stay high. Buildings and concrete that absorbed heat during the day remain warm overnight, and the next day begins from a higher thermal baseline than the last. This is the ratchet effect of a heat dome. Each day increments warmer than the one before, not just because the forcing is continuing, but because the starting point is elevated. Day 1 of a heat dome event is survivable for most people in most circumstances. Day 3 is dramatically more dangerous. Day 5, in a region without air conditioning, without night cooling, without infrastructure designed for the event, can be lethal for thousands. Researchers studying the 2021 event identified an additional mechanism that amplified the heat beyond what standard atmospheric models predicted. A 2024 paper published in PNAS by a research team examining resonant planetary wave amplification found that the 2021 event involved quasi-stationary planetary waves, waves in the jet stream that span the globe, amplifying in a resonance pattern that existing climate models do not accurately capture. The waves became effectively trapped within a mid-latitude waveguide, producing anomalously high amplitudes in ways that compound the standard omega block dynamics. The researchers concluded that climate models, by underrepresenting this resonance mechanism, are likely underestimating the future frequency and severity of events like 2021. Researchers studying the 2021 event identified an additional mechanism that amplified the heat beyond what standard atmospheric models predicted. A 2024 paper published in PNAS by a research team examining resonant planetary wave amplification found that the 2021 event involved quasi-stationary planetary waves, waves in the jet stream that span the globe, amplifying in a resonance pattern that existing climate models do not accurately capture. The waves became effectively trapped within a mid-latitude waveguide, producing anomalously high amplitudes in ways that compound the standard omega block dynamics. The researchers concluded that climate models, by underrepresenting this resonance mechanism, are likely underestimating the future frequency and severity of events like 2021. The waveguide narrowing that enables this resonance is itself a product of Arctic amplification. The well-documented phenomenon of the Arctic warming at roughly 4 times the global average rate due to feedback mechanisms, including sea ice loss. As the temperature difference between the Arctic and the mid-latitudes decreases, the jet stream becomes less energetic, more prone to large amplitude meanders, and more susceptible to blocking. The planetary waves that drive those meanders amplify more easily and persist longer before the atmosphere's normal restoring mechanisms push them back toward zonal flow. The blocking events that produce heat domes become more persistent. The omega blocks become more durable. The heat accumulates longer before relief arrives. Then there is the soil moisture feedback. Sayede Mahia Bartusek, Kai Kornhuber, and Mingfang Ting, researchers at the Lamont Doherty Earth Observatory, published an analysis in 2022 examining the role of soil moisture in amplifying the 2021 event. Their findings: nonlinear interactions between atmospheric circulation, soil moisture depletion, and the warming baseline amplified the severity of the 2021 event by approximately 40%, beyond what the atmospheric dynamics alone would have produced. Dry soils reduce the amount of energy that goes into evaporating water, a process that cools the surface, and redirect that energy into heating the air directly. A separate analysis by Zhang and colleagues found that heat extremes under blocking circulation patterns intensify faster than the background warming rate. When global mean temperature rises by 1 degree Celsius, associated maximum temperatures under dome conditions rise by 1.75 degrees, not 1. The amplification is nonlinear. What this means practically is that the official temperature forecast, already alarming at 30 to 40 degrees above average, is a model output that does not incorporate the full cascade of amplifying feedbacks. The physical understanding of these events has advanced to the point where atmospheric scientists know that the forecast is more likely to be an underestimate than an overestimate when all of these reinforcing mechanisms are in play. The region arriving into the current event is not entering from a position of soil moisture resilience. It is entering from one of the worst winters on record. The winter of 2025 to 2026 across the Pacific Northwest and Intermountain West was not merely dry. It was historically anomalous in its warmth and aridity across much of the region, producing conditions that, heading into the heat event now forecasting, constitute the worst possible starting point for what is about to arrive. Daniel Swain, a weather and climate scientist at the University of California, Los Angeles, whose atmospheric analyses are widely cited across the meteorological community, stated explicitly in March of 2026, "We are about to experience the hottest March temperatures that we've ever seen across a lot of the western U.S. He added, regarding the possibility of a late winter precipitation rescue, a lot of folks like to talk about the notion of a miracle March. This year, that is not going to happen. His assessment was confirmed. The last week of March 2026 produced what the National Weather Service and NOAA climate analysts documented as the most expansive March heat wave in American history. Over 7,000 daily temperature records and approximately 2,000 monthly records fell over the course of that event. Yuma, Arizona reached 109 degrees Fahrenheit, a new national March record, beating a mark that had stood since 1954. As that early season heat event concluded, the inventory of what it left behind was damaging. Denver Water reported that South Platte Basin snowpack had reached just 54% of normal on March 16th, the worst on record for that date. The Bureau of Reclamation's forecast for inflow to Lake Powell projected April through July runoff at just 36% of average, the fifth lowest in the 63-year forecasting history. NOAA's Climate Prediction Center, in its spring 2026 outlook, identified the Pacific Northwest, Great Basin, Central Rockies, Southwest, and South Central Plains as facing the highest probabilities of above-normal temperatures and drought expansion. John Gottschalk, chief of the Operational Prediction Branch at NOAA's Climate Prediction Center, noted in that outlook that the combination of a warmer and drier than average winter had worsened or created drought across multiple regions of the country. What this means for the heat dome now arriving over the Pacific Northwest is the soil moisture feedback that the Bartusek research quantified. The topsoil of the Pacific Northwest and British Columbia, ground that in a normal spring would be holding winter's accumulated moisture, feeding the green fire-resistant biology of the temperate forest, providing the evaporative buffer that moderates surface temperatures during warm spells, is depleted. Evapotranspiration rates from the spring warming have extracted moisture that has not been replenished. The drought monitor, as of mid-spring 2026, showed the broader western United States at 61% coverage of moderate or worse drought conditions, up from 56% just weeks earlier. Dry soil under a heat dome does not moderate temperatures. It amplifies them. The energy that should go into evaporating soil, moisture instead, goes directly into heating the surface air. That 40% amplification factor the Bartusek team identified, the additional severity conferred by soil moisture depletion on top of the atmospheric dynamics, is not an extreme case scenario for the current event. It is the baseline condition the event is arriving into. There is a term for what happens when a heat event arrives at this scale, at this speed, in a region that was already drought-stressed, flash drought. The United States Drought Portal, operated by the National Integrated Drought Information System, defines flash drought as the rapid onset or intensification of drought set in motion by abnormally high temperatures, lower than normal precipitation, abnormal winds, and changes in radiation. What distinguishes flash drought from conventional drought is speed. Conventional drought develops over months or seasons, giving agricultural and water management systems time, imperfect but real, to identify and respond. Flash drought can go from early onset to severe conditions in 2 weeks, sometimes faster. The mechanism during a heat dome is straightforward and relentless. High temperatures drive evapotranspiration, the combined loss of water through evaporation from the soil surface and transpiration through plant leaves, at rates that can strip topsoil moisture in days. The Council on Foreign Relations Flash Drought Analysis, published in February 2026, just months before the current event, noted that flash droughts have gained increasing attention from researchers and policymakers precisely because they compress warning time and scramble response interventions in ways that conventional drought does not. The CFR analysis cited the 2010 Russian flash drought, which contributed to 11,000 excess deaths and produced a wheat export ban that cascaded through global food markets, as an example of the systemic reach of these events. The Pacific Northwest forest, arriving into a heat dome with depleted soil moisture, is not the same system that navigated previous heat events. It is drier, more stressed, more vulnerable to the one thing that a heat dome, a flash drought, and a tinderbox forest together reliably produce. The relationship between a heat dome, a flash drought, and wildfire risk is not sequential. They are simultaneous, mutually reinforcing processes that compound within days of each other. When topsoil moisture vanishes under extreme heat and the absence of precipitation, the first thing to change is the forest understory. The grasses, the shrubs, the low vegetation that in a well-watered spring constitutes a living moisture-retaining ground cover, desiccates. It turns from green to brown, from high moisture biology to dry organic material with roughly the ignition characteristics of paper. This transition, which in a normal fire weather progression might take weeks to months, can occur in 4 to 7 days under the evaporative forcing of a heat dome. The moisture content of fine fuels, the grasses, small twigs, and leaf litter that are the kindling layer of any wildfire, is measured by foresters and fire behavior analysts using the energy release component, a composite index of fuel moisture and temperature. When fine fuel moisture falls below 10%, fire behavior transitions from manageable to extreme. Under a heat dome with temperatures running 20 to 30 degrees above normal, fine fuel moisture can drop below 10% within a week, even from a relatively well-watered starting point. From a drought-depleted starting point, the transition is faster. The living trees themselves are not immune. Unlike fine fuels, large trees take longer to lose their moisture, but under extreme and sustained heat, they begin to lose it too, and a stressed tree is far more likely to ignite and carry fire into the forest canopy. The 2021 heat dome produced documented mass mortality events among trees across the Pacific Northwest and British Columbia, not from fire, but from direct heat damage and associated bark beetle outbreaks that targeted moisture-stressed trees. Those dead trees, killed by the 2021 event, and still standing in the forest across British Columbia, Oregon, and Washington, are now 5 years of additional dry fuel load waiting in the landscape for the next ignition. AccuWeather meteorologist Tom Keynes articulated this dynamic in the context of the March 2026 early season heat event, warning that one concern we have about this early season heat wave across Southern California is it will cause the ground cover to brown up much earlier than usual, which could spell trouble and increase the fire danger. He was speaking of Southern California specifically, but the mechanism is identical for the Pacific Northwest. An early season heat event that desiccates the landscape creates a fire weather setup that persists well into the season, even after the heat event itself concludes. The damage to soil moisture and fuel moisture from the current dome will not be repaired by a single subsequent rain event. It will be carried forward into the fire season. The British Columbia wildfire season of 2023 shattered Canadian records, burning over 18 million hectares, by far the largest area burned in Canadian recorded history, in a season driven by the convergence of drought, early season heat, and the legacy fuel load from previous fire seasons and the mass tree mortality of 2021. A Nature Communications paper analyzing the 2023 Canadian fire season, published in 2024, attributed the record season to the interaction of anomalous heat, drought, and antecedent fuel conditions, the same three-way compound that is assembling over the Pacific Northwest right now. And while the fire risk is extreme, it is not the most immediate threat this event carries. That distinction belongs to what happens when tens of millions of people without air conditioning try to survive temperatures 40 degrees above what they are physiologically prepared for. The human body is a thermal engine. It runs at approximately 37 degrees Celsius, 98.6 Fahrenheit, and it maintains that temperature through a suite of mechanisms that collectively constitute thermoregulation. Perspiration is the primary active cooling tool. Sweat glands produce moisture that evaporates from the skin surface, removing heat from the body through the physics of evaporative cooling. Vasodilation, the widening of blood vessels near the skin, increases blood flow to the surface, where the blood can release heat to the surrounding air. The heart works harder, pumping more blood per minute to support both physical function and the thermoregulatory effort. These mechanisms work well when the environmental temperature is below body temperature and when the air is dry enough for sweat to evaporate efficiently. They work increasingly poorly as air temperature climbs toward and above body temperature, and they begin to fail when the wet bulb temperature, the temperature a surface can reach through evaporative cooling, which combines air temperature and humidity, exceeds the body's ability to maintain its cooling rate. At wet bulb temperatures above 35 degrees Celsius, which corresponds to roughly 120 degrees Fahrenheit, at low humidity, or significantly lower temperatures at high humidity, the human body cannot cool itself effectively, even through maximum sweating. Core temperature climbs. Organ systems begin to fail in sequence. This is heat stroke, and it kills. The Pacific Northwest population is physiologically unprepared for the temperatures now forecast in a specific way that has nothing to do with infrastructure and everything to do with biology. Acclimatization, the physiological adjustment to hot conditions that includes increased plasma volume, earlier onset of sweating, and improved cardiovascular efficiency under heat load, takes approximately 10 to 14 days of gradual heat exposure to develop. The Pacific Northwest, in late spring, has not produced that gradual exposure. The transition from cool, marine-influenced temperatures in the 60s and low 70s to forecast temperatures of 95, 100, 105 degrees or higher will happen in days. The bodies of people living in this region arrive at those temperatures without the adaptations that populations in Phoenix or Houston carry as a matter of routine. This is the physiological equivalent of asking someone who has never run before to complete a marathon at race pace. The system is capable of the effort in principle. The human body can survive extreme heat, but not without the preparation that makes it capable. The lack of acclimatization is what turned the 2021 heat dome from a severe weather event into a mass casualty incident. During the 2021 event, Portland International Airport exceeded 100 degrees Fahrenheit for 3 consecutive days, 108 on June 26th, 112 on June 27th, and 116 on June 28th. The previous all-time record at Portland International was 107 degrees. Salem Airport reached 117 degrees on June 28th. Oregon's Center for Health Statistics reported 123 deaths in Oregon directly attributable to the heat wave. 62 of those deaths occurred in Multnomah County alone, the county that contains Portland. Total deaths across Oregon, Washington, Idaho, and Canada exceeded 900, with over 600 of those in British Columbia alone. The USDA climate hubs documented at least 250 excess deaths in the United States and more than 400 in Canada. The 63-fold increase in heat illness emergency department visits in Oregon during the event is a number worth parsing. Not 63 more visits than normal. 63 times normal. Emergency departments not designed for mass casualty incidents were simultaneously processing hundreds of heat stroke patients, with the resource competition and triage challenges that entails. The vast majority of those who died, both in the emergency departments and in the homes where they were found, died in non-air conditioned settings. Many were found alone. The current forecast runs 30 to 40 degrees above seasonal averages for the Pacific Northwest. Seasonal averages for late spring in Seattle and Portland are in the 60s and low 70s. 30 to 40 degrees above that puts forecast temperatures between 100 and 112 or above at the peak of the event. Not a cooler version of 2021. A near replica of it, arriving into a population that the intervening years have not fully equipped with air conditioning, arriving into a grid system that was formally assessed in 2025 as being on the edge of reliability during extreme weather events, and arriving into a landscape that is drier and more fire vulnerable than the one 2021 burned. There is one more dimension of physiological vulnerability that deserves explicit attention, because it shapes who is most at risk and why public health systems so frequently fail to reach them in time. A substantial fraction of the heat-vulnerable population, particularly the elderly and people with chronic conditions, is on medications that impair thermoregulatory function in ways their prescribing physicians may not have flagged as a heat emergency consideration. Diuretics, commonly prescribed for heart failure and hypertension, increase fluid loss and accelerate dehydration. Beta blockers, used for heart conditions and anxiety, suppress the cardiovascular response to heat stress and reduce the body's ability to increase heart rate to meet thermoregulatory demand. Antipsychotic medications can impair the hypothalamus's ability to regulate body temperature directly. Antihistamines reduce sweating. Anticholinergic drugs, prescribed for bladder control, overactive bladder, and other conditions, reduce sweat gland activity. These drug-heat interactions are documented in medical literature and well known to emergency medicine physicians and pharmacologists. They are not well known to the patients taking the medications. The elderly person on 3 or 4 chronic condition medications who believes they are managing their health appropriately arrives at a heat emergency physiologically compromised in ways they have no awareness of. They may not feel particularly hot because the medication has blunted their body's alarm signals. They may not sweat, and so may not drink additional water. They may not recognize that they are developing heat stroke until cognitive impairment from rising core temperature makes self-rescue impossible. This is the demographic and pharmacological profile that produced the mortality pattern of 2021. It is the same profile entering the current event. And the public health intervention that reaches this population, the welfare check, the direct outreach, the proactive cooling, is exactly the intervention that has consistently been identified as underfunded relative to the scale of the vulnerable population it needs to serve. The most dangerous fact about a heat dome arriving over the Pacific Northwest is not the temperature. It is the combination of the temperature and what proportion of the population has no mechanical way to reduce it inside their homes. The U.S. Census Bureau's American Housing Survey provides the most reliable data on residential air conditioning rates by metropolitan area. At the time of the most recent comprehensive survey, roughly 44% of households in the Seattle metropolitan area had air conditioning, either central air or window units. That figure made Seattle the least air-conditioned major metropolitan area in the United States, ranked last among the 15 largest metros measured. The remaining 56% of Seattle households had no mechanical cooling. For Portland, the figure was better, but still dramatically below the national norm. Approximately 79% of Portland area homes had air conditioning as of 2019, a figure that had doubled from the 43% measured in 2002, reflecting the post-2021 acceleration in AC adoption. But 21% of Portland metro homes still lack any cooling system. In a city of roughly 2 million people in its metropolitan area, that is roughly 400,000 households, entering a major heat event with no mechanical protection. The national air conditioning rate for the United States is 91%. In Phoenix, Houston, Miami, and New Orleans, air conditioning coverage approaches or exceeds 98%, effectively universal. Those cities have hot climates that historically demanded cooling infrastructure, and their building stock, their electrical systems, and their utility planning all reflect that demand. The Pacific Northwest had mild summers for most of its modern development history. The buildings were not designed for cooling. The electrical system was not planned around peak cooling demand, and the culture did not develop the same reflexive relationship to air conditioning that marks population centers where it is a survival necessity. The Seattle Times analysis of the demographic dimensions of the AC gap found patterns that track with exactly who died in 2021. Seattle homeowners are nearly twice as likely as renters to have air conditioning. Households with 6-figure incomes are more likely to have AC than those with lower incomes, but even a majority of Seattle area households with 6-figure incomes do not have it. Critically, only 37% of people aged 65 and older in the Seattle area have air-conditioned homes. Seniors are physiologically more vulnerable to heat. Their thermoregulatory efficiency declines with age. Their cardiovascular reserves are smaller, and they are more likely to be on medications that impair heat tolerance, including diuretics, beta blockers, and antipsychotics. 37% with AC, among the most heat-vulnerable population group. 63% without. The 2021 event made clear that the relationship between AC coverage and survival is not abstract. The mortality pattern was specific. The people who died were disproportionately elderly, disproportionately living alone, and disproportionately in homes without air conditioning. They were not found in hotels or cooling centers. They were found in their own homes, in conditions where the indoor temperature had climbed to levels that exceeded their body's ability to survive. the cooling center strategy, the public health intervention of opening libraries, community centers, and other public buildings as air-conditioned refuges during heat events, is the standard municipal response to the AC gap. It is better than nothing. It is not, by itself, adequate. The 2021 event demonstrated that a significant portion of the at-risk population did not use cooling centers, either because they were unaware, because they were unable to travel to them safely, or because they chose to stay home. People found alone in non-air-conditioned homes were not failing to follow the advice to go to a cooling center. They were in the conditions that make following that advice impossible. Too old, too sick, too isolated, or too proud to ask for help until it was too late. Before this heat event arrived, before a single household in the Pacific Northwest had switched on an air conditioner in response to a temperature that had crossed the survival threshold, the electrical grid serving the region was already formally assessed as inadequate for extreme conditions. In October 2025, a report commissioned by the Public Generating Pool, a trade organization of Northwest Utilities, and conducted by the consulting firm Energy and Environmental Economics, known as E3, was released. The report analyzed the Pacific Northwest's energy plans against potential weather and hydropower conditions across Washington, Oregon, Montana, Idaho, and parts of Utah and Wyoming. It simulated over 2,500 years of energy demand and generation scenarios to determine when outages would be most likely. Its findings were clear enough that the region's utility community spent the final months of 2025 in a state of concentrated concern. The power reliability gap in the greater Northwest, defined as the shortfall between available generating capacity and peak demand during extreme weather conditions, was estimated at approximately 1,300 megawatts in 2026. For context, 1,300 megawatts is roughly the output of a large nuclear power plant running at full capacity. By 2030, the E3 report projected that gap would grow to approximately 8,600 megawatts, roughly the entire electricity load of the state of Oregon. In a dry hydropower year, combined with a days-long extreme weather event, the report found the probability of rolling blackouts in the region reached levels that utility planners classify as a resource adequacy crisis. The Pacific Northwest's electrical grid relies heavily on hydroelectric generation from the Columbia and Snake River systems, a generation source that is directly dependent on snowpack and precipitation patterns. The record low snowpack that marked the winter of 2025 to 2026 directly constrained the available hydropower. The Bureau of Reclamation's forecast of April through July inflow to Lake Powell at just 36% of average is the same low water condition that the E3 report identified as the primary amplifier of grid vulnerability. The BPA, the Bonneville Power Administration, the federal agency that operates 15,000 circuit miles of transmission lines across the Northwest and markets power from the federal hydroelectric system, was aware of these constraints during the 2021 event. At that time, BPA Transmission Services Senior Vice President Richard Shaheen described the agency's response. We've put all maintenance projects that we can on pause to ensure our transmission system can handle increased flows and meet our customers' demands. The agency transitioned fish spill operations on the lower Columbia and Snake Rivers from spring to summer protocols to increase hydropower generation. It positioned Grand Coulee Reservoir to meet its refill target early. The Columbia Generating Station, a 1,207 megawatt nuclear unit in Benton County, Washington, was brought back online from its spring refueling outage to provide additional generation. All of that effort resulted in rolling blackouts anyway. Oregon and Idaho utilities urged conservation during peak time events. Portland General Electric grappled with outages. The TriMet Max light rail system in Portland suspended service because the heat exceeded the design limits of its overhead power cables, melting them. Sections of Interstate 5 and State Route 162 in Washington buckled, causing lane closures. That was 2021, when the grid's formal reliability assessment had not yet been completed, when the E3 report had not yet been written, when the gap was smaller than it is today, because the coal plant retirements that have since occurred, and the data center load growth that has since accelerated, and the failure of replacement generation to match the pace of demand growth had not yet compounded to today's level. Opalco, Orca's Power and Light Company, an island utility cooperative in Washington, published an analysis noting that the E3 simulations showed the loss of load probability for the Northwest grid at 12.8% in 2024, reaching 26% in 2026. 26%, more than 1 in 4 simulated years, based on realistic weather and generation scenarios, produces a grid failure under current conditions, and those simulations were built on historical weather patterns. A heat dome event 30 to 40 degrees above average is not in the historical pattern baseline. It is a tail event applied to a system that is already at the edge of its capability under normal tail events. The specific mechanism that would trigger rolling blackouts during this heat dome is not complicated. As temperatures climb into the 90s and 100s, the population reaches for cooling. Air conditioner sales surged after 2021. Portland's AC rate went from 43% in 2002 to 79% in 2019 and has continued climbing. Each additional percentage point of AC coverage that has been added since 2021 represents additional load on the grid during exactly the events that drove that adoption. The demand curve during a major heat event is steep and sudden. Utilities designed around moderate peak loads see their headroom evaporate in hours as temperatures cross thresholds that turn AC from optional to essential. And when generation cannot meet demand, the protocol is exactly what the E3 report described: rolling load shedding, neighborhoods taken off the grid on rotating schedules, power cut to the places that need it most at exactly the moment the need is greatest. The Pacific Northwest's electrical generation system has a feature that most of the country's systems do not. It is overwhelmingly powered by water. The Columbia River system, anchored by Grand Coulee Dam in Washington, the largest hydroelectric facility in the United States by generating capacity, and its network of tributary dams, produces the majority of the electricity consumed in the region. In a water normal year, hydropower is a reliable, clean, and abundant resource that gives the Pacific Northwest one of the lowest carbon electrical grids in the country. In a drought year, or specifically in the low snowpack, early runoff year that follows the warmest winter in Western history, that dependency becomes a vulnerability. Hydropower generation depends on water volume behind the dam. Water volume behind the dam depends on snowpack, accumulated over the winter and released as the snowpack melts in spring and early summer. When the winter is warm and dry, snowpack is low. When an early season heat event melts, what little snowpack exists ahead of schedule, the water arrives at the reservoir early before summer demand peaks, and the reservoir begins to draw down earlier in the season. By the time the heat dome arrives in late spring or early summer, the water is already running thin. Grand Coulee Dam can generate up to 6,765 megawatts under full flow conditions. Under low water conditions, typical of a drought year, its effective output can be significantly reduced. The BPA and the Bureau of Reclamation manage the reservoir system to balance multiple competing demands: power generation, irrigation, water delivery to agricultural users, fish passage requirements for salmon and steelhead, and flood control. During a heat event, the power generation imperative conflicts with all the others simultaneously. More water through the turbines means more power, but it also means faster drawdown of a reservoir that is already below normal levels, with consequences for the rest of the season's water budget. The salmon and steelhead passage requirements add a specific constraint that does not exist in most grid systems. Federal biological opinions governing the management of the Columbia and Snake River dams require minimum river flows and temperature conditions to protect endangered Pacific salmon populations. When the river runs low and warm during a heat dome, fish passage requirements can limit the rate at which the BPA can draw down reservoirs for power generation. The fish and the power grid are in direct resource competition, managed by a regulatory framework that the heat dome neither knows about nor respects. The 2025 E3 report found that a dry hydropower year, defined as a year in which the Columbia River system operates at reduced capacity due to below-average snowpack and runoff, was the single most important amplifying factor for grid vulnerability. Combine a dry hydropower year with a heat event that spikes demand, and the gap between what the grid can supply and what the region needs closes quickly. The winter of 2025 to 2026 has been a dry hydropower year, in the specific sense the E3 report was designed to evaluate. The snowpack numbers are in. The runoff forecasts are published. The condition that the report identified as the primary blackout risk amplifier is the condition that is now present. The Columbia Generating Station, the 1,207 megawatt nuclear unit at the Hanford site in Benton County, Washington, marketed by BPA, is one of the grid anchors that utility planners count on during heat events precisely because its output does not depend on wind, sun, or water. In 2021, BPA brought the Columbia Generating Station back online from its spring refueling outage specifically to provide generation during the heat dome. Having that unit available or not having it available due to a scheduled maintenance window can represent the difference of over a gigawatt of dispatchable generation at the exact moment the grid needs it most. And while the grid is fighting its hydropower constraint, the other generation sources in the Pacific Northwest are having their own weather-related limitations tested. Wind power, a growing component of the region's electricity mix, with most new capacity built in Wyoming and Utah, is driven by pressure differentials that can collapse under heat dome conditions. High-pressure systems, by definition, are regions of suppressed wind. An omega block over the Pacific Northwest is simultaneously a heat threat and a wind drought. Solar power, the other major renewable addition to the regional grid, does not compensate well. While solar performs well on clear days, the peak demand during a heat event often comes in the late afternoon and evening after peak solar generation has begun to decline. The grid's ability to call on interstate power imports, purchasing electricity from California, the Southwest, and the Rockies to supplement regional generation, is also constrained during heat events, because those regions are often simultaneously experiencing their own high demand conditions and have less surplus power available for export. When electrical power fails during a heat emergency, it does not fail cleanly, it cascades. The immediate consequence of a rolling blackout during a heat dome is obvious. The air conditioner stops. For households that have cooling, the loss of power resets their protection to zero. But the failure cascade extends well beyond individual residences. Hospitals and medical facilities operate on backup generator systems that are designed for short-duration outages, typically rated for 72 hours of fuel supply, with assumptions about resupply logistics that may not hold during a regional emergency. Extended outages that outlast generator fuel supplies compromise temperature-sensitive medication storage, medical equipment requiring continuous power, and patient monitoring and life support systems. The 2021 event did not produce extended hospital outages, but it did overwhelm emergency rooms with a 63-fold surge in heat illness visits, and it did that without simultaneously cutting hospital power. The combination, surging demand and reduced capacity, represents a qualitatively worse crisis than either alone. Water systems also depend on electricity. Water treatment plants, pumping stations that maintain pressure in urban distribution systems, and wastewater treatment facilities all require continuous power. When grid power fails, facilities that do not have backup generation lose pumping capacity. Water pressure drops. In extreme cases, extended outages, failed generators, depleted fuel supplies, municipal water systems can lose pressure entirely, which has consequences both for fire suppression and for the tens of thousands of people who will be attempting to cool themselves through hydration during the peak of a heat emergency. Refrigeration failure has health consequences that compound during a heat event. Insulin and other temperature-sensitive medications have storage requirements that ambient heat rapidly violates. The population of diabetic patients who rely on refrigerated insulin across the Pacific Northwest is not small. Nationally, roughly 1 in 10 Americans has diabetes, and insulin-dependent diabetics face a medical emergency if their insulin supply becomes non-viable due to heat exposure during a power outage. food safety collapses within 4 hours of refrigeration failure, adding foodborne illness risk to a population already under heat stress. Cell networks, internet infrastructure, and emergency communication systems rely on backup power at individual tower and data center locations. Most have between 4 and 24 hours of battery backup before requiring generator support. A multi-day rolling blackout scenario in a heat emergency, the scenario that the E3 report simulations produced when they combined a dry hydropower year with an extreme weather event, is a scenario in which the communications infrastructure that coordinates the emergency response begins to degrade at exactly the moment when the coordination is most critical. Texas winter storm. Uri, in February 2021, demonstrated what happens when a grid system encounters weather conditions beyond its design limits. More than 200 people died. Millions lost power for days in freezing temperatures. The failures were not random. They cascaded through interconnected infrastructure systems in ways that no single failure analysis had anticipated. The Pacific Northwest heat dome scenario differs in its specific weather trigger and in its population vulnerability profile, but the underlying dynamic is identical. Extreme weather, a grid near its capacity limits, and the compound failures that emerge when multiple systems push simultaneously against their design margins. And this is where the story takes a turn that most heatwave coverage does not follow. Because the compounding of these three threats, a lethal heat dome, an unprotected population, and a grid on the edge of failure, is not happening independently of the broader context of how the Pacific Northwest arrived at this moment. It is the product of a specific sequence of decisions, deferred investments, and planning choices made against a backdrop of changing climate risk that has been documented in increasing detail for over a decade. The March 2026 early season heat event, the most expansive March heat wave in American history, the event that broke over 7,000 daily temperature records, was analyzed in real time by atmospheric scientists who noted its mechanistic similarity to the June 2021 Pacific Northwest heat dome. The diabatic engine analysis, published in mid-March 2026, examining the physics of what was then an active event over the southwestern United States, identified the key mechanism, downstream ridge amplification, driven by upstream latent heat release, the same process that built the 2021 dome. The atmospheric machinery that produces these events is not a random perturbation. It is a physics engine that climate scientists have been describing in increasing mathematical detail since the 2021 event generated more than 70 peer-reviewed papers attempting to explain it. The research consensus from those papers includes several findings that bear directly on the current situation. First, the resonant planetary wave amplification mechanism that contributed to the 2021 event's extremity is becoming more prevalent as a result of Arctic amplification associated with greenhouse forcing. The warming of the Arctic at roughly 4 times the global average rate, which is narrowing the mid-latitude waveguide and making blocking events more persistent. Second, the soil moisture feedback that amplified the 2021 event by 40% is, if anything, stronger in the current event because the drought baseline is more severe. Third, the diabatic ridge amplification mechanism is self-reinforcing through ocean surface temperature feedbacks. A warmer ocean surface destabilizes the marine boundary layer, reducing the cool marine air that normally moderates Pacific Northwest temperatures, even when pressure ridge patterns push warm air into the region. These are not speculative projections. They are mechanisms that have been observed, analyzed, and published in peer-reviewed literature since 2021. The question is not whether the physics is real. The question is whether the understanding of that physics has been translated into the infrastructure, the preparedness systems, and the public health capacity that a region facing repeated events of this type requires. The answer that the E3 report, the AC coverage statistics, and the 2021 mortality data together provide is not completely, not yet, and not in time for what is arriving now. A heat dome of this character does not arrive at its worst immediately. It builds. And understanding the hour-by-hour progression of what it does to unprotected human bodies, to regional infrastructure, and to the landscape is essential for understanding both the scale of what is coming and the specific windows where intervention remains possible. On day one of a major heat event, temperatures climb into ranges that are uncomfortable and stressful, but not immediately lethal for healthy adults. In the high 80s and low 90s, the human thermoregulatory system is working hard, perspiring, vasodilating, elevating heart rate, but managing. The night, if temperatures drop into the 60s or below, provides recovery. Cardiovascular stress accumulated during the day is relieved. The body resets to near its resting state. Core temperature, which may have climbed a fraction of a degree during peak heat, returns to normal. Sleep is disrupted but possible. On day two, the starting temperature is higher. The recovery window is shorter. Buildings that absorbed heat the previous day begin the new day warmer. Concrete, which has a high thermal mass, releases its stored heat slowly and enters the next day already preheated. Wood frame structures without insulation rated for keeping heat out. The reverse thermal function from what Pacific Northwest homes were designed for, which is keeping heat in during cool winters. Heat up faster and cool down slower than their occupants expect. By day three, the ratchet has closed significantly. Nighttime lows are not low enough to provide full recovery. People who have been spending their physiological reserves on thermoregulation for 2 days arrive at the third day already depleted. Dehydration accumulates. The cardiovascular system, which has been running elevated output for days to support thermoregulation, begins to show strain. For the elderly, for people with heart disease, for people on medications that impair heat tolerance, day three is where the transition from serious medical stress to medical emergency occurs. The 2021 event, which lasted from roughly June 25th through June 29th, 5 days of above record temperatures, produced most of its deaths in the third through fifth day of the event. The people who died were not overwhelmed immediately. They were worn down. Their thermoregulatory systems failed, not in an instant, but over a period of hours, in rooms that had been climbing in temperature for days, without the cooling respite that a functional air conditioner or a genuinely cool night would have provided. This is the ratchet effect applied to human physiology at the population scale. The hospitals that will receive heat stroke patients on day 4 of the event are receiving them after those patients have already spent 3 days in thermal stress. 3 days of cardiovascular strain, dehydration, and disrupted sleep that have depleted physiological reserves. The emergency department that saw 63 times its normal heat illness volume in Oregon during 2021 was seeing the accumulated effect of a ratchet that had been tightening for days before the peak. Those patients were not all acute cases who had just become ill. Many were people whose slow physiological deterioration over multiple days had crossed into emergency territory on day 3 or day 4. The physiological cascade of heat stroke, hyperthermia, the elevation of core body temperature above 40 degrees Celsius, follows a sequence that emergency medicine knows well. As core temperature climbs, the brain begins to malfunction. Confusion sets in. The judgment that would lead a person to call for help or move to a cooler location is impaired by the very condition that requires those actions. Hot, dry skin replaces sweat. The sweating mechanism fails under severe hyperthermia, removing the body's primary cooling tool at exactly the moment it is most needed. Organ systems begin failing in sequence: the kidneys, the liver, the cardiovascular system. Without active cooling, cold water immersion, ice packs to the groin, and armpits, intravenous fluids, the interventions that emergency departments provide, heat stroke is fatal within hours. The 63-fold surge in heat illness emergency department visits in Oregon during 2021 reflects the number of people who reached or approached this cascade and required intervention. The mortality statistics, 900 or more deaths across the region, reflect those who did not receive intervention in time, or who were found only after the cascade had progressed beyond the point of survival. The temperatures that weather stations record, official maximum and minimum temperatures, are measured in standardized conditions. In the shade, at a standard height above the ground, away from paved surfaces and buildings. Those measurements are already alarming during a major heat dome. The actual temperatures that human bodies experience in urban environments are substantially higher. The urban heat island effect is well-documented physics. Cities replace vegetation, which evapotranspires and cools, with pavement, concrete, and buildings, which absorb solar radiation and re-emit it as heat. The difference between urban temperatures and surrounding rural temperatures can be 5 to 15 degrees Fahrenheit or more under heat dome conditions. And within cities, the difference between tree-canopied neighborhoods and exposed, dense, low vegetation neighborhoods can be similar. King County, Washington, the county that contains Seattle, released a heat vulnerability map in the period following 2021 that showed less affluent neighborhoods where tree canopy cover is low and impervious surface coverage is high, experiencing the dangerous effects of heat more acutely than their more affluent counterparts. This is a documented geographic disparity in heat exposure that the official temperature statistics do not capture. The official temperature at SeaTac Airport may read 102 degrees. The temperature at street level in a dense, low canopy neighborhood of Seattle may be 112. Building materials compound the effect. The asphalt shingled roofs of Pacific Northwest homes absorb solar radiation intensely, heating attic spaces to temperatures that can exceed 150 degrees Fahrenheit under direct sun exposure during a heat dome. That heat radiates downward into living spaces. Buildings without attic ventilation, buildings with poor insulation, or insulation designed to hold heat in, not keep it out, can have interior temperatures that significantly exceed outdoor temperatures by mid-afternoon on day 2 or 3 of a heat event. The people dying inside their homes during the 2021 event were dying in rooms where the temperature may have been higher than the outdoor maximum. The overnight recovery problem is amplified in urban heat island conditions, while rural areas and suburban neighborhoods with substantial tree cover can drop into the upper 50s or low 60s on a summer night even during a heat event. Dense urban cores can remain in the upper 70s or 80s overnight. The concrete and asphalt that absorbed heat all day release it through the night, keeping the ambient temperature elevated until after midnight, at which point sunrise is only a few hours away and the cycle begins again from a higher floor. Portland's north and northeast neighborhoods, historically lower income areas with lower tree canopy density, recorded some of the highest heat illness rates during 2021. The mortality data from Multnomah County, which produced 62 of Oregon's 123 documented heat deaths, was concentrated in exactly these urban heat island zones. The people most vulnerable, elderly, low income, without AC, also tend to live in the urban zones where the heat is worst. The intersection of the vulnerability map and the heat exposure map is not random. It is the predictable outcome of a century of development patterns that prioritize some neighborhoods over others in ways that now translate directly into differential survival during extreme heat. The forecast models showing temperatures 30 to 40 degrees above average for the Pacific Northwest represent the output of numerical weather prediction systems. Computer models that simulate the atmosphere's physics using observations from thousands of surface stations, weather balloons, aircraft, and satellites as their initialization data. Those models have become dramatically more accurate in the last 2 decades. Their skill at 7-day temperature forecasts has improved to the point where a prediction issued today for conditions next week has roughly the reliability that a 3-day forecast had a generation ago. But there are things the forecast models do not capture, and those gaps matter enormously for understanding what the current event will actually produce. The models predict official temperatures. The shade measured standardized height temperatures that weather stations record. They do not directly predict the urban heat island increment, the building interior temperatures, the asphalt surface temperatures, or the wet bulb temperatures that determine human survivability. Converting a model forecast of 102 degrees at SeaTac Airport into a prediction of what humans in a top-floor Seattle apartment without AC will experience requires additional analysis that most public-facing heat forecasts do not provide. The models also do not predict human behavior and its interaction with the electrical grid. When a model shows temperatures reaching 100 degrees in Portland, the model is not simultaneously computing the surge in air conditioner demand that will result, the impact of that surge on the grid, the probability of rolling blackouts, and the resulting feedback effect on indoor temperatures in neighborhoods that lose power. Those second-order effects, the compound consequences of the primary weather event interacting with the physical and social infrastructure of the region, are where much of the mortality in heat events is produced, and they require a different kind of analysis than meteorological modeling provides. The resonant planetary wave amplification mechanism identified in the 2021 post-event analysis is a specific example of a physical process that current generation forecast models do not fully capture. The PNAS paper on that mechanism noted explicitly that it is not well represented in state-of-the-art climate models, and that neglecting such preconditioning feedback mechanisms in climate model analyses could potentially cause underestimates in the future likelihood or severity of extreme continental heat waves. If the model cannot fully resolve the mechanism that amplifies the event to its worst extreme, the model's forecast of the event's intensity may be a systematic underestimate. Daniel Swain, the UCLA climate scientist, uses a communicative framework for heat events that distinguishes between what the models show and what the physics permits. For the March 2026 early season Western heat event, Swain's analysis emphasized that the atmospheric setup was capable of producing temperatures that exceeded even the model forecasts, because the compounding feedbacks, soil moisture, ocean temperature, ridge amplification, are not fully captured in the operational forecasting systems. His caution proved warranted. The March event produced records that exceeded pre-event model forecasts in multiple locations. There's an additional model limitation specific to the Pacific Northwest that deserves mention. The local topography of the region, the Cascades to the east, the Coast Ranges to the west, the complex interplay of Puget Sound marine influence and continental interior air masses creates local meteorological features that operational forecast models at their standard resolution do not fully resolve. Downslope winds from the Cascades, air that descends from altitude, compressing and warming as it does, can push temperatures in Seattle and the greater Puget Sound lowlands significantly above what the regional model fields suggest. The phone effect, as this type of wind is known, was a documented contributor to temperature amplification during 2021. Portland sits in a valley configuration that produces its own thermal amplification. The official model forecast temperature is an area averaged value for a model grid cell that may be tens of kilometers on a side. The actual temperatures at specific locations within that grid cell can vary by 5 to 15 degrees depending on local topography, land cover, and wind patterns. The same caution applies to the current event over the Pacific Northwest. The model forecast is the floor estimate. The actual event can exceed it. There is a specific dismissive framing that attaches itself to heat wave stories, and because it circulates in good faith among people who are genuinely confused rather than in bad faith among those who are deliberately misleading, it deserves a direct response grounded in the science. The argument is this: heat waves have always happened in the Pacific Northwest. The region gets hot sometimes. The 2021 event was unusual, but unusual events happen. The attention given to heat events is disproportionate to the actual risk, driven by media sensationalism and climate anxiety rather than data. This is just weather. Let's address each component of this directly. Heat waves have always happened in the Pacific Northwest. This is true. The historical record includes documented heat events in the mid-20th century and earlier. What has changed is not the existence of heat waves, but their intensity, frequency, and the context into which they arrive. The Science Advances paper that placed the 2021 event at over 4 standard deviations from the historical mean was measuring that deviation from the full range of the observational record. The event was not an outlier from the recent record. It was an outlier from everything ever measured. Climate attribution science, the field that uses counterfactual climate modeling to estimate how much more or less likely specific extreme events are under current climate conditions versus pre-industrial climate conditions, has published a formal attribution for the 2021 event. The assessment, The event was at least 150 times more likely to occur in the current climate than in the pre-industrial climate. A separate attribution analysis concluded that the 2021 heat dome would have been virtually impossible without human-caused climate change. The Pacific Northwest has warmed by 3 to 4 degrees Fahrenheit since the pre-industrial period, a warming that researchers including Paul Loy-Keith at Portland State University, who has written the authoritative summary of the 2021 event for Oregon Encyclopedia, have documented across the long-term temperature record at Portland International Airport and other stations. Climate scientists studying the 2021 event in peer-reviewed publications have projected that if greenhouse gas emissions continue on their current trajectory, events of similar severity will occur every 5 to 10 years in the Pacific Northwest by mid-century. 5 to 10 years. Events that in the pre-industrial climate had a return period measured in tens of thousands of years, if they were possible at all, becoming features of the regular climate cycle within the lifetime of children alive today. And finally, the mortality. 900 people died across the Pacific Northwest and British Columbia in 5 days during June 2021. Not from a hurricane, not from an earthquake, not from a disease outbreak, from hot air. The characterization of that as just weather requires treating 900 deaths as an acceptable weather-related norm. They were not. They represented one of the most lethal weather events in North American history, unprecedented in the region, and produced in part by a physics mechanism that is becoming more common as the background climate state evolves. This is not a drill. This is not sensationalism. This is the documented physics of what heat domes do in regions that are not prepared for them, arriving into exactly those conditions. The honest assessment of what the current heat dome forecast means requires presenting 3 interpretations that are each consistent with portions of the available evidence and being clear about which the weight of the data most supports. Interpretation 1. The current forecast event, while severe, will fall within the range of outcomes that the Pacific Northwest's evolving preparedness capacity can manage without a catastrophic failure. Air conditioning rates have improved dramatically since 2021. Portland has gone from 43% in 2002 to 79% as of the most recent comprehensive data, and Seattle has been climbing steadily. Cooling centers are better staffed and better publicized following the 2021 experience. Utilities have pre-positioned resources and implemented conservation programs. The public health messaging about heat vulnerability is more effective than it was in 2021 because the event that generated the messaging actually happened to this population within living memory. Under this interpretation, the event produces significant heat illness and some mortality, but at a lower rate than 2021, the grid manages with controlled conservation efforts rather than uncontrolled blackouts, and the region's post-2021 investments in resilience produce measurable results. This interpretation has genuine supporting evidence. The AC adoption increase in the Pacific Northwest since 2021 has been real and substantial. Improved public awareness is a legitimate variable. Better cooling center logistics and more aggressive public health outreach do reduce mortality in heat events compared to the no warning baseline. The utilities have contingency protocols that did not exist before 2021. These are real improvements. Interpretation? 2. The current event produces mortality and infrastructure stress broadly similar to 2021 because the improvements in preparedness have not kept pace with the changes in both the climate forcing and the grid vulnerability. The AC adoption increase, while real, still leaves hundreds of thousands of households in the Seattle and Portland metro areas without cooling, disproportionately in the most heat-vulnerable demographics. The grid vulnerability documented by the E3 report is a real-time constraint that cannot be improved before the event arrives. The drought-depleted soil moisture creates a compounding amplification factor that the official forecast temperatures do not fully capture. Under this interpretation, the event produces casualties in the hundreds. Rolling blackouts affect meaningful portions of the urban population at peak heat, and the wildfire conditions set up by the flash drought extend the event's consequences well beyond the heat dome's duration. Interpretation. 3. The current event represents a qualitative step beyond 2021 in its total system stress because the compound conditions, record drought baseline, grid vulnerability formally documented at critical levels, early season heat that has already primed the flash drought, and the resonant amplification mechanism that current models may be underestimating, interact in ways that produce an outcome worse than the direct forecast temperatures suggest. In this interpretation, grid failures are widespread rather than limited. Wildfire ignitions under flash drought conditions occur during or immediately following the heat dome, and the cascade of failures, power, water, communications, medical, produces a public health emergency that exceeds the region's response capacity. The evidence most strongly supports interpretation. 2. With the elements of interpretation 3 that are most directly grounded in the documented grid vulnerability. The E3 reports 26% annual loss of load probability for 2026, representing a genuine risk rather than a worst-case speculation. What distinguishes this event from a straightforward repetition of 2021 is the grid. The mortality in 2021 occurred with the grid mostly intact. The deaths happened in homes without air conditioning, not in homes where the air conditioner was running when the power went out. If the E3 report's analysis is correct, and it was commissioned by the utilities themselves using their own data with full knowledge of the stakes, then the current event arrives with a grid that is more vulnerable than 2021's was, into more demand than 2021 created with less hydropower buffer. The interaction of those three factors with the heat event itself is where the current situation exceeds the 2021 template. Let's be precise about the epistemology of this event. What is established versus what remains uncertain. What is established? Forecast models as of mid-May 2026 show a significant high-pressure ridge building over the Pacific Northwest, with temperature anomalies in the range of 30 to 40 degrees Fahrenheit above average at peak. The seasonal average high temperatures for late May in Seattle are approximately 65 to 68 degrees Fahrenheit. 30 to 40 degrees above that puts forecast peak temperatures between 95 and 108 degrees, with some localized areas potentially exceeding that range under urban heat island and downslope wind conditions. What is established? The Pacific Northwest population's residential air conditioning rates leave between 20 and 56% of households, depending on the specific city, without mechanical cooling, with the unprotected households disproportionately occupied by the elderly, by renters, by lower income households, and by other groups with elevated heat vulnerability. What is established? The E3 Energy Consulting Report, commissioned by the region's utilities and released in late 2025, documented a resource adequacy gap of approximately 1,300 megawatts in 2026 that creates a meaningful probability of rolling blackouts during extreme weather conditions, particularly during a dry hydropower year. What is established? The winter of 2025 to 2026 was historically anomalous in warmth and dryness across the western United States, producing record low snowpack in multiple mountain ranges and a drought baseline entering spring that is more severe than the baseline entering any previous major Pacific Northwest heat event. What is established? The resonant planetary wave amplification mechanism, documented in the 2021 post-event literature, is a physical process that current generation forecast models underrepresent, meaning the model forecast temperatures for the current event may be systematic underestimates. What is not established? Whether this event will match, exceed, or fall below the 2021 mortality toll. That depends on variables that are genuinely uncertain, the precise peak temperatures in specific urban heat island zones, the performance of the electrical grid under the actual demand curve, the effectiveness of public health interventions, behavioral responses, and whether the rolling blackout scenario materializes and to what extent. What is not established? Whether wildfire ignitions will occur during or immediately following the heat dome, and if so, what their extent will be. The flash drought conditions make ignition more likely and fire behavior more extreme if ignition occurs, but the specific ignition events are not predictable in advance. What the data has also established, and what rarely appears in weather-focused heat event coverage, is the agricultural dimension of the compound event. The flash drought that a heat dome of this character triggers is not only an ecological and wildfire risk phenomenon, it is a crop and livestock emergency with economic consequences that extend far beyond the event itself. The Pacific Northwest is one of the most productive agricultural regions in the United States. The Willamette Valley of Oregon produces a significant share of the nation's grass seed, hazelnuts, and wine grapes. Eastern Washington is the dominant producer of apples and cherries in the United States. The Columbia Basin produces potatoes, wheat, and a broad range of vegetables at an industrial scale. A flash drought arriving during the critical growth window of late spring, when crops are emerging and soil moisture is essential for root establishment, can cause yield losses that do not manifest in a single catastrophic day, but accumulate invisibly over weeks, as heat-stressed plants fail to set fruit, as drought-stressed soil cannot support normal growth, and as irrigators strain against water allocation limits that a low snowpack year has already constrained. The agricultural community of the Pacific Northwest is entering the current event with the same depleted water budget that the grid managers and public health officials are navigating. They are watching the same drought monitor. They are calculating the same deficit. The honest summary, the inputs to this event, the atmospheric setup, the drought baseline, the population vulnerability, and the grid constraint are all in the range that produced a mass casualty event in 2021. Some of those inputs are worse than 2021's. Some are better. The net outcome is genuinely uncertain within a range that includes both a managed difficult event and a catastrophic one. The science of heat emergencies has progressed substantially since 2021. We know what saves lives during extreme heat events. The question is whether the response system can deploy those interventions at the speed and scale required. The most effective single intervention in a heat emergency is active cooling for at-risk individuals who lack home cooling. This means more than opening cooling centers. It means proactively reaching people who will not reach the cooling center on their own. The elderly living alone, the homebound, the people who are too proud, too confused, or too physically compromised to self-identify as at risk and seek help. Post-2021 analyses of the mortality data consistently found that the people who died were largely not reached by the community outreach systems that were operating during the event. They were found after the fact. Reaching them in advance, door-to-door wellness checks, pre-positioned cooling resources in the buildings where heat-vulnerable populations live, direct outreach to home health agencies, and senior service organizations is what changes the mortality outcome. For the electrical grid, utilities in the Pacific Northwest have demand response programs that incentivize customers to reduce consumption during peak periods and interruptible rate contracts with large industrial users who can be asked to curtail demand in exchange for lower rates. The BPA has emergency protocols for calling on neighboring grids for emergency power imports. These mechanisms work at the margins. They do not solve the fundamental resource adequacy gap documented by the E3 report, but they can delay or reduce the severity of load shedding events during the critical peak hours of a heat event. For wildfire, pre-positioning of fire suppression resources, aerial tankers, hand crews, engine companies, in areas where the flash drought conditions and expected lightning or ignition activity create elevated risk is the standard incident command approach. The National Interagency Coordination Center coordinates this positioning nationally. The Northwest Coordination Center handles the Pacific Northwest region. The decisions about pre-positioning are informed by the same drought monitor data and temperature forecasts that this investigation has been examining. What all of these interventions have in common is that they require lead time. The door-to-door wellness check program cannot be staffed and deployed in 12 hours. The demand response programs require enrolled customers who have opted in before the event, not during it. The fire resource pre-positioning requires crews and equipment that are currently distributed across the national inventory to be repositioned based on a forecast that is days in advance. The interventions that can still materially affect the outcome of this event are the ones that are being activated now, before peak heat arrives. Every hour of that lead time that is used productively corresponds to a subset of outcomes that shift from the catastrophic end of the range to the managed end. The specific population that represents the highest risk and most difficult to reach group is not hard to identify. It is elderly people living alone in homes without air conditioning in urban neighborhoods with low tree canopy cover. Those individuals check every box on the vulnerability profile: physiologically vulnerable, pharmacologically compromised, socially isolated without mechanical cooling in the environments where urban heat island amplification is worst. The post-2021 analyses found that this group represented a disproportionate share of the mortality precisely because they were not visible to the standard emergency response systems until someone found them after the event. The technology now exists to pre-identify this population at the city block level. Heat vulnerability mapping, the kind King County released after 2021, combined with utility billing data that identifies households without air conditioning, combined with Medicare records of elderly single-occupant households, can produce a map of where the highest risk individuals are before the event peaks. Several Pacific Northwest jurisdictions have been developing exactly these tools since 2021. Whether the tools have been developed to the point of operational deployment and whether the staffing exists to act on them at the required scale is the question that the outcome of this event will answer. The city and county public health offices of Seattle, Portland, Eugene, Olympia, and their Canadian counterparts in Vancouver and Victoria are the front line of the response system. Their capacity, staffing, funding, equipment, coordination with utilities and emergency management determines what can actually be deployed in the next 72 hours. Public health budgets that were adequate for normal operations are stretched severely by a simultaneous mass casualty heat event and grid emergency. The post-2021 investments in those capacities will now be tested against the event that drove the investments. A heat dome of this character is not an isolated event in a stable climate. It is a data point in a trend that atmospheric scientists have been characterizing with increasing precision since the 2021 event generated the research community's intensive post-event analysis. The California Water Research blog analysis of the March 2026 early season Western heat event identified a structural shift in North American winter circulation patterns, what it characterized as the leading mode of North American winter circulation having changed, producing conditions in which the atmospheric machinery that builds heat domes forms more reliably in the same geographic location, with less upstream forcing required to trigger it. The waveguide has narrowed. The background state in which the diabatic ridge amplification mechanism operates has shifted. The same machinery that produced the 2021 Pacific Northwest heat dome, the 2020 Siberian heat wave, and the 2019 and 2022 European mega heat waves is working more efficiently in a warmer background climate, producing events of record-shattering severity with higher frequency. The climate attribution research community has quantified this shift for the Pacific Northwest specifically. The 2021 event, assessed as at least 150 times more likely in the current climate than in the pre-industrial climate, was not the new normal. It was a demonstration of what the new normal will produce as the background temperature continues to rise. If current greenhouse gas trajectories continue, events of 2021 severity could occur every 5 to 10 years in the Pacific Northwest by mid-century. If the background warming continues to accelerate beyond current trajectory projections, that interval compresses further. That trajectory means that the decisions being made right now about the electrical grid's resource adequacy, about building codes for heat resistance, about tree canopy in urban neighborhoods, about AC adoption, about the cooling center network, about the water infrastructure's backup power systems, are not responses to a one-time exceptional event. They are foundational infrastructure decisions for a region that will face events of this class repeatedly, potentially annually within a generation. The grid vulnerability documented by the E3 report, the 1,300 megawatt gap in 2026, growing to 8,600 megawatts by 2030, is not a weather problem. It is an investment problem. The gap exists because the retirement of coal generation capacity in the Pacific Northwest has outpaced the addition of replacement capacity that is reliable during extreme weather conditions. Coal is carbon intensive, and its retirement is both appropriate and legally mandated by Washington's clean energy law. But the replacement for wind, solar, and the long-duration storage or dispatchable generation that makes variable renewables reliable during heat domes, when wind dies and solar peaks before demand does, has not been built fast enough. The E3 report was not a political document. It was a resource adequacy analysis commissioned by the utilities themselves because they needed to know where they stood. Where they stood in 2025 was at the edge. NOAA's El Niño monitoring, as of late April 2026, showed 85 to 94% probability of El Niño conditions being present through summer 2026, up from 62% just weeks earlier. El Niño's influence on the Pacific Northwest is well documented. Drier and warmer summers relative to neutral conditions, with elevated fire season risk, reduced snowpack, and above average probability of blocking ridge events that produce heat domes. The background climate is changing. The natural variability driver, El Niño, is loading in the direction that amplifies the same risks the background change is increasing. These are not independent factors pointing in opposite directions. They are aligned. What this alignment produces in practical terms is a compounding risk calendar that extends well beyond this single heat event. If the heat dome causes or accelerates flash drought conditions, those conditions persist through the summer fire season, regardless of whether the heat dome itself breaks. If wildfire activity occurs during or following the dome, the smoke that fire generates adds its own health burden to a population already stressed by heat. Smoke from large wildfires contains fine particulate matter, PM2.5, at concentrations that cause cardiovascular and respiratory stress even in healthy individuals, and that is particularly dangerous for the elderly, children, and people with chronic lung disease. The 2021 heat dome was followed by a severe fire season. The 2023 British Columbia fire season burned 18 million hectares under analogous compound conditions. The Pacific Northwest in 2026 is entering the same compound risk corridor. The Teton Gravity Research Spring 2026 drought analysis noted that as the region heads into July and August, soil moisture in Montana, Idaho, and eastern Washington is expected to remain critically low, potentially leading to trail closures and water restrictions earlier than seen in recent high snowpack years. Those are the recreational and water management consequences. The wildfire consequence of the same soil moisture deficit is the one that the emergency management community is watching most closely. We will be watching the development of this heat dome in real time, and we will cover the outcomes as the event unfolds. The metrics that matter, whether peak temperatures match or exceed the forecast, whether the grid maintains reliability through the peak demand hours of the first 96 hours, whether the cooling center and wellness check systems reach the at-risk population effectively, and whether wildfire activity emerges from the flash drought conditions in the days following peak heat. The public utility districts of Washington and the investor-owned utilities of Oregon, Portland General Electric, Pacific Power, Puget Sound Energy, Avista, will be issuing conservation appeals, and in the grid failure scenario, rolling blackout notifications through their standard communications channels. The National Weather Service offices in Seattle and Portland are issuing heat warnings and advisories. The Northwest Interagency Coordination Center is managing fire resource positioning. The public health offices are activating cooling center networks. All of it will be covered here with the same investigative attention to the gap between what is being said publicly and what the data actually shows. Because that gap, the distance between our grid is managing and the 26% annual probability of failure documented by the utility's own consultants, is exactly the kind of gap this channel exists to examine. Not to alarm people needlessly, not to predict outcomes that the evidence doesn't support, but to give you the full picture of what the science, the engineering reports, and the monitoring data say, rather than the summarized and optimistic version that institutional communications tend to offer during developing emergencies. If you're in the Pacific Northwest right now, or if you know someone who is, the most useful thing to do with the next 24 hours is also the simplest. Check on the people in your life who are elderly, who live alone, and who you're not sure have air conditioning. Don't call and ask if they need help. Assume they do. The ones who need help most are often the ones least likely to ask for it. 2021 was largely a disaster of isolation. People found alone after it was too late. The intervention that changes that outcome is not a government program. It is a phone call, or better, a visit. It is a neighbor who shows up before the worst day, not after. The heat doesn't know who it's coming for. We do. And we'll be here, watching all of it, telling you what the data shows as it develops. That's the commitment. The dome descends. The grid strains. The ground is dry. We're watching.